All right, I'm awake.
Oh, hey, you're up. I had an idea for our next episode that I wanted to run by you.
Huh? Oh, yeah, sure. Give me a chance to wake up a little, would you? And then we can chat.
Yeah, no problem. I'll go finish what I was watching and then come back.
Oh, what are you watching? Anything good?
Yeah, this Tom Cruise movie, Edge of Tomorrow. Ever seen it?
Oh, sure. It's really good. Tell you what, you go finish the movie and we can chat afterwards.
Bing! See you in a few.
Bing. You know, come to think of it, I'm still kind of tired. Hey, Noah, I think I'm going to nap a little longer. Wake me up when you're done with that movie.
I got you. Okay, campers, rise and shine, and don't forget your booties, 'cause it's cold out there today.
Nice going, guys. You already played that bit.
Oh, hey, you're up. I had an idea for our next episode that I wanted to run by you.
Yeah, I remember. Is your movie over already?
My movie?
Aren't you watching that Tom Cruise movie in the other room?
No.
Wait, you didn't come in here a minute ago and say that you were watching Edge of Tomorrow?
No. I was going to watch that, but then I saw that Run Lola Run was available, and I've never seen it, so I started that instead. Besides, you were snoring away in here a minute ago. You probably dreamed it.
Okay, yeah, you're probably right.
And you still sound pretty sleepy.
Yeah, I am. I'm going to nap a little more while you finish your movie, and then we can talk about the podcast.
Bing!
Bang, what is going on here?
I got you.
Okay, what is going on here?
Oh, hey, you're up. I had an idea for our next episode that I wanted to run by you. How did you know that?
The same way I know what you're watching on TV in the other room.
Okay, I'll bite. You knew I was watching Russian Doll.
Russian. Wait, I thought you were watching Run Lola Run.
No, I was going to watch that, but then I saw that Russian Doll was available, and I've never seen it, so I started that instead. How do you keep doing that?
You're not going to believe this, but I think I'm stuck in a time loop. I've had the same conversation with you 3 times now. We need to figure out how to get me unstuck.
Whoa, just like Russian Doll.
Yeah, and come to think of it, also just like Edge of Tomorrow and Run Lola Run. It seems that each time I go through this, you're watching something different about time loops.
That is weird. I wonder if that's the only thing that's changing each time, maybe the shows and movies are a clue as to how we can help you.
Oh, good idea. In time loop movies, the person usually gets out of it by finally doing something right.
Hmm, that's discouraging for you then.
Ha ha.
But seriously, what are you doing each time the loop resets?
Let's see. You come in and tell me you have an idea for a new episode of the show. Then you go back to finish what you're watching, and I lay down on the couch to finish my nap. Next thing I know, Sonny and Cher are playing on the radio, and I'm waking up and starting it all over.
Okay, so let's do that differently. How about if instead I tell you my idea and then we go ahead and record the new episode?
It's worth a shot. What's your idea?
Well, ironically, I got the idea from the show I was watching. Just like the main character in Russian Doll, you're bouncing around the space-time continuum, and it made me wonder if there's any math that has to do with space-time that we might discuss.
Oh, there's loads to talk about. I think that'd be a great topic for an episode. And you know what? I'm not looping back in time. So maybe this is the universe telling us we should definitely talk about space time.
Bing!
I got you.
Hey, everybody. Welcome to another episode of the Math Club. Happy New Year to all of you out there listening. Noah, how you doing?
Oh, I am doing pretty well. Had a great holiday break. Happy to be back here in the Math Club. Really happy to be talking about something that seems Right up my science fiction loving alley.
Yeah, I figured this would be kind of your deal. I mean, like you said, you're a huge sci-fi fan, so this sounds like it's totally your bag.
It totally is. But I got to admit something before we get too much further in. As a certified card carrying member of the Nerd Club, I have definitely heard the term space time over and over and over again in all kinds of media, books, movies, TV shows. They're always talking about the space time continuum. But my admission is I'm not totally sure what it actually is. Like, is the space-time continuum a physical thing? Is it just sort of a mental construct? Is it an idea? What is it, Pete?
Yeah, it is well, to put it simply, no, it's a four-dimensional smooth manifold with a Lorentzian metric and a curvature tensor.
All
By
right. Well, thanks everybody, and we'll see you next time.
Okay, I think we should start from a slightly simpler vantage point than what that big reveal would suggest. So let's slow things down a little bit. We were getting awfully close to 88 miles an hour there. How about we start like this? The way I'm using the term space time, I mean a mathematical model. And in particular, it's a four-dimensional geometric gadget that physicists and mathematicians use to study the universe.
Okay, so let me apply some of what I think I've learned from you in past episodes and see if I'm applying it right. When you say it's a model, that takes me back to our episode Model Behavior, where we talked about the Petri multiplier. And in that context, a model was kind of a mental construct that represented something in the real physical world. And then we used that model by putting different values or numbers in and seeing how it reacted so that we could kind of predict how whatever it represents in the real world might react. Is that the same way we're talking about a model here?
Yeah, I mean, it certainly shares certain things in common with that description you just gave. Here's another way to think about it. So we all know that the Earth is not perfectly spherical. In fact, it's of course has hills and valleys
No McFly ever amounted to anything in the history of Hill Valley.
and mountains and an ocean and all sorts of surface geography. But even beyond that, at its core, it's not spherical. It's close to a sphere, but it's something called a geoid. And yet, we can really do a nice job understanding the Earth by imagining that, in fact, modeling it as though it were a perfect sphere. And that's sort of the approach that I am getting at here when I say that space time is a four-dimensional geometric gadget.
Gotcha. And I think I speak for all of our listeners when I thank you for saying geoid and not gooeyoid.
All right, Gooey Duck, I get your point. Let's keep going.
All right. Well, this takes me back to what I've always heard, which is that time is the fourth dimension. Can we talk about that for a minute? I know that we have three spatial dimensions, length, width, and height. And we always say that time is the fourth dimension. So, in what way is that fourth dimension like the other three? And in what ways is it different from those three?
You're just not thinking fourth dimensionally.
Right, I have a real problem with that.
Well, that's a good question. And it is like the other three in that it is parameterized by a real number. So we could imagine that at every moment in time, we're thinking of some real number that counts units of time. And so just as we might have real number coordinates in space, we could similarly have a fourth real number coordinate representing time. But the time dimension is really different. In fact, oftentimes when people are referring to the four dimensions of space-time, they call it 3+1 dimensions because they're really trying to denote the fact that time is special and different. And there are ways that the mathematics itself reflects this difference.
That's really interesting. Like, what's an example of one of those ways?
Well, let's go back in time, if you will, to the middle of the 17th century. So we're talking the time of Isaac Newton. Galileo has already lived his life and had made a number of significant contributions to our understanding of mathematics and physics. And now Isaac Newton has been handed the baton and is now pushing forward with calculus, namely his mathematical theory of change. And he is very interested in taking Galileo's observations to the next level. At this time, Galileo and Newton would have thought of time in a very particular way. Namely, time is this universal clock.
A company
Is like an enormous clock.
is like an enormous Yes, precisely.
It's the same for everybody. We might have individual clocks and watches that are out of sync with this universal clock, but in principle, the idea would be that we could all synchronize to it. Time is the same for everybody, effectively, and it's universally available. And the mathematics that they carried out reflected that particular philosophy of time.
All right, that all makes sense to me. And I think there's a very natural and logical reason why scientists, mathematicians, and even your common everyday people from Newton's time would have made that conclusion about time. That's certainly what it looks like when you look at it, doesn't it?
Yeah, exactly. And in fact, well, that's certainly the way I experience it in my day-to-day life. And I assume that would have been even more the case back in the 17th century prior to the invention of technology we have that might give us some reason to think time behaves differently.
Sure. But just to elaborate a little, what I mean is I'm down here in the Bay Area, you're up in Washington. We can talk on the phone. And if I say to you, hey, I'm going to hang up and I'm going to call you back in 15 minutes, I can rest pretty easy knowing that 15 minutes for you is the same thing that 15 minutes is for me.
Yeah, and I'm glad you brought up this idea of you being in the Bay Area and me being up here in Seattle. That opens the door for a conversation about frames of reference. And so you might think of your position down in the Bay Area. You might say, well, wherever you happen to be, that's the origin of space. So coordinates 0, 0, 0 are where Noah is, and everything else is measured relative to that origin. So relative to that frame, my X, Y, and Z coordinates are on the order of hundreds of miles, right? So my X coordinate might be, depending on how you've oriented your frame, my X coordinate might be 800 miles, and my Y coordinate might be 137 miles, right? And similarly, the reverse would be true if I had a frame of reference here in Seattle where I was at the origin. Then I would measure you as being 800 some miles away in various directions. And herein is the beginning of some of the work that both Galileo and Newton were doing in the 17th century.
Okay, but I would also say that if we then add in a fourth coordinate of time, and I say that where I am and when I am is the origin, 0, 0, 0, 0, that even though you're in a different X, Y, and Z coordinate from me, we share that same 0 on our, let's call it our T coordinate for time.
Yeah, and so if we were to translate the coordinates between one of our frames and the other, the transformation that happens between time would simply be your time coordinate T is equal to my time coordinate, let's call it T prime. Whereas you have X, Y, and Z spatial coordinates, I might have X prime, Y prime, Z prime coordinates, and they would be different relative to one another. But essentially, they would have the form of X prime is equal to X minus 800, Y prime is equal to Y plus 137, Z prime is equal to Z plus 15, depending on how high above sea level we are.
Right.
But there would be no translation for the time coordinates. T prime equals T. That was Newton's assumption. That was Galileo's assumption.
And that would be the same regardless of where you were. You could be 800 miles away, you could be in orbit around the planet, or you could be on an interstellar starship booking through space. All of those, according to Newton, our time coordinates would be moving along at the exact same rate as each other.
Yeah, that's right. And as you point out, it could happen if our frames of reference were moving relative to each other. Now, I'm assuming, you're relatively stationary, I'm relatively stationary, but we could imagine, and in fact, let's do imagine a situation that, anyone who's opened up a physics textbook is going to be familiar with this example. So let's say that you're standing next to a railroad track and I come sailing by on a train.
The train leaves the station at 8 Monday morning. We'll stop it here, uncouple the cars from the tender, throw the switch track, and then we'll hijack, borrow the locomotive.
And so your frame of reference is stationary, sitting there with you at the origin. And To keep things simple, let's imagine that there's just an x coordinate, and let's imagine that there's just then a time coordinate. We'll forget the y and z coordinates for a moment. So you're sitting at x equals 0, and at some moment in time, let's say t equals 0, that's the moment when I come sailing past on my rail car.
Okay, so when t equals 0, that's when x and x prime are the same. That's when we're in the same x location. Leading up until the moment you get there, x prime is something negative. After you sail on past me, x prime is something positive. But right at t equals 0, x equals x prime.
Yeah, and that's in your coordinate system. In my coordinate system, x prime is 0 the whole time. Time is t prime. And from my point of view, however, it might start off that x is positive, and when I go sailing past you, now x is negative.
That's really interesting because you're the one that's moving, but you're presenting it as if from your frame of reference, you're just kind of hanging out still and the whole universe is sort of moving around you.
Right. And this is exactly how frames of reference work, right? And there's no such thing. You might think like, but wait a second, Pete, my frame is the stationary one. And I would say, really? Because if I was like out in space looking down at Earth, you'd be booking past me with the rotation of the Earth. You would not be in a stationary frame. So your frame is stationary relative to the rotation of the Earth and the movement of the Earth around the sun, but it is absolutely not stationary in some universal sense.
Okay, good point. Good point. Let's keep going.
So let's suppose now that you and I are both interested in carrying out some sort of physics within our frames of reference. And I'd like to think about Newton's second law of motion, which is that force is equal to mass times acceleration. So F equals ma. This is something that, anybody who's studied physics in high school or college is certainly familiar with. And we can ask, how does F equals ma? How does that formula look when interpreted within our different frames of reference? So in your frame of reference, you perform some calculation and you get F equals ma. But now I'm in the prime reference. So I would have to know, what is F prime and A prime? Is it still the case that F prime equals M A prime? And the answer is yes. Newton's laws work identically well within these two reference frames, that when I transform coordinates from your system to mine by performing the subtraction that we were just talking about, x being negative or positive relative to x prime and vice versa, when I perform those transformations, which by the way are called Galilean transformations, I find out that F equals ma in both of our coordinate frames. It's the same thing.
Okay, forgive my sounding like a total layperson here, but is that unusual that we find that?
Well, it's really good news, because if the laws of physics depended on your frame of reference, then the laws wouldn't feel very universal, would they? I mean, it would be like, well, F equals ma, unless here's a long list of caveats.
Now, what you need now is either a king and a deuce, except at night, of course, when you need a queen and a four.
Except at night.
Right.
Okay, I get what you're saying, but I also think I am predicting where we might be heading, because although I don't know a lot about relativity, I know that the relative in relativity means that things are not always the same depending on your frame of reference, that they can be relative. So is all of this also true when we move further down the timeline and we start getting to Einstein and what he started to talk about?
Well, you're getting a little bit ahead of things, but that's okay, because I think now's a fair time to jump forward into the 19th century. And Maxwell, James Clerk Maxwell, who was studying electricity and magnetism as well as light, was able to unify those two forces into a single electromagnetic force with his so-called Maxwell's equations. And this is a system of four different equations that relate the electric field and the magnetic field to one another. And just like with Newton's laws, he was very interested in how those laws transformed between frames of reference. And unfortunately, there was some bad news.
What was the bad news?
That even under very basic Galilean transformations, like you standing next to the railroad and me sailing past in my rail car, the transformations led to two different formulations of Maxwell's equations. They are not invariant with respect to Galilean transformations.
Oh, woe is the world of mathematics when Maxwell comes on the scene.
Well, it would be pretty woe as all of us because our modern world, which harnesses electromagnetism, is really based on our understanding of those laws and how they do transform from one coordinate system to another. So this was kind of a very sad day for everybody. And, it led people to wonder, well, is there something wrong with Maxwell's equations? Is there something that we don't understand with the universe? I mean, they seemed to work really well, but there was this transformation problem. So maybe there's something about the universe that we don't understand. Maybe we're just not doing the mathematics right, or we don't have a complex enough model. Think about when mathematicians and physicists were trying to perform the calculations to show that the sun went around the earth. Boy, a lot of special weird stuff had to be factored in, and the math was getting incredibly complex. And then Galileo said, maybe we've got it wrong, and it's the earth that goes around the sun. And bam, the math became a lot better.
I'm assuming that something similar to that happened here, that someone came along and said, we're looking at it wrong. It's really like this.
Yeah. And that was Einstein and others, chiefly Einstein. And what it boils down to actually is the speed of light. And Einstein said, we only need to add one additional physical law, and that is that the speed of light is constant in every frame of reference.
Yeah, I've heard that, but I'm not sure I really understand it because the whole thing feels a little counterintuitive whenever I try to do a thought experiment about it in my head.
Jesus Christ, Doc, you disintegrated Einstein.
Yeah, so let's simplify things back to our railcar example. And suppose that as I'm sailing towards you, let's say I'm going, I don't know, 25 miles an hour in my little putt-putt rail car here, and I've got an orange that I've decided I'm going to toss to you when I get close. And so I wind up and I throw it at you. And, I looked this up. An average speed for throwing something is about 50 miles an hour, at least if you're not like a pro baseball pitcher. So I throw this to you at 50 miles an hour from my little car. Okay. The question is, how fast is that orange going to seem to you when you receive it?
Well, I think that it's going to be going the 50 miles per hour that you threw it, plus the 25 miles per hour of inertia that it already had from being in that car when you let go. So I think it's going to hit me at 75 miles per hour.
And you're absolutely right. That is what's going to happen. Let's suppose, on the other hand, that I'm cruising along in my rail car at 25 miles an hour and it's nighttime. And I think to myself, where's Noah? I can't see him. I'm going to turn on my flashlight. So I do. And I shine my flashlight at you and I see you. How fast is the light going to appear to you as it's coming at you from my flashlight?
Well, if it behaves the same way as the orange, it's going to be the speed of light plus 25 miles per hour, just a tiny, tiny bit faster than the speed of light. But that's where it all breaks down because I know we've all heard that the speed of light is a universal speed limit and nothing can go faster than the speed of light.
You're right. You will also, in your frame of reference, measure that light as going exactly the speed of light.
And what will you measure it as from your frame of reference?
Also the speed of light.
Isn't that weird?
It is weird, but it's been experimentally verified. In fact, we've known this for over 120 years. And just so listeners can have this number in their heads, the speed of light is roughly 186,000 miles per second, or almost 300 million meters per second. That's pretty fast.
That is very fast. We could define that as pretty fast.
So now, as soon as you add in this little bit of physics, it requires you to look at your transformation laws between frames of reference differently. And the kind of transformation that we need to employ is now no longer these Galilean transformations, but some new kind of transformation that incorporates velocity and the speed of light in a particular way. And these are the so-called Lorentz transformations.
Okay, and what are those about?
So they introduce a new factor, a multiplier into both the spatial coordinates, but also the time coordinate. And so now we are forced to reckon with the fact that there is no universal clock and that I can no longer say that t prime, which is time in my coordinate system, is equal to t, which is time in your coordinate system. The time variable also needs to transform in accordance with these Lorentzian laws of transformation.
And when we allow that to happen, then suddenly Maxwell's equations start making sense again?
Maxwell's equations behave beautifully with respect to Lorentz transformations. And in fact, in his famous 1905 paper introducing the theory of special relativity, Einstein spends much of the beginning of that paper demonstrating these transformation laws in terms of Maxwell's equations. So this was very much on the mind of everybody back in the day, but in particular, Einstein was also bothered by this problem of transformation law. And why weren't Maxwell's equations transforming properly? Well, we were using the wrong laws of transformation. Essentially, we were neglecting the speed of light.
And the world of mathematics rejoices when Einstein comes on the scene.
Truly, high fives all around.
That's a really cool story, Pete. I love the fact that Maxwell came in with these equations and they just seemed right, but they weren't accurately predicting what the universe was going to behave like. And instead of the answer being that the equations were wrong, the answer was we were looking at the universe wrong. And when Einstein came along and said, look at it like this, all of a sudden everything became clear again.
But if you turn it the other way,
Everything becomes clear.
Yeah, and now we're seeing a glimpse into why the concept of space-time, because the Lorentz transformations no longer allow time to be this independent universal coordinate. They say, not so fast. Time transforms just as spatial coordinates must, and they do so using a particular factor called the Lorentz factor. And I actually think that Lorentz factor, although a little complex, might be worth talking about.
Yeah, let's hear about it.
All right, so I'm going to tell you mathematically what this factor looks like, and then we'll be able to derive a couple of consequences from it, okay?
Yeah.
It's usually called gamma, the Greek letter gamma, and it's a ratio. The numerator is very simple. It's simply the number 1. And now in the denominator, there's a very particular square root. You ready for it?
Yeah.
All right. I want you to take the number 1 and subtract from it the quantity v squared divided by c squared. All right. So 1 minus v squared over c squared.
All that's in the denominator under 1.
It's actually also under a square root sign. So it's 1 over the square root of 1 minus v squared over c squared.
And what's v in this context?
V is the velocity at which one reference frame is moving relative to another. So, for example, in the rail car scenario, I am moving relative to you at 25 miles per hour, right? That's my V.
That's v. And c, of course, is the speed of light. So in this case, we would say 1 over the square root of 1 minus 25 squared over the speed of light squared.
Yeah, you'd have to get the speed of light in the right units. If 25 is miles per hour, we'd want to make sure that c was also expressed in miles per hour. But let's notice a couple of things. We already know the speed of light is 186,000 miles per second. And in 1 hour, there are 3,600 seconds. So the speed of light in terms of miles per hour is huge. And now square it. And that is the denominator of this fraction, this little guy in there, where v squared is 25. It's 625 divided by a bajillion.
So that
125
denominator is almost 1.
Yes. 1 minus something that is very close to 0 is practically equal to 1. The square root of something very close to 1 is also close to 1. And 1 over essentially 1 is 1. In this case, this Lorentz factor is practically equal to 1. It's so close to 1 that we couldn't even tell by a hair's breadth.
I'm the one and only one. El numero uno.
And that's because v is such a small number compared to the speed of light. So I'm guessing that as your velocity starts getting faster and faster and faster, up to something approaching the speed of light, that's when we start to see this number really change.
Yes, it also explains why at the kind of velocities that we experience in our day-to-day life, we never really get a chance to witness the Lorentz factor in action. So of course we thought the Galilean transformations were correct. We just had no direct experience with this other effect.
That makes sense. That's really cool. I love it when you can look at the math and sort of see how it all works.
Yeah, now something else interesting happens. We've got this square root of 1 minus v squared over c squared in the denominator. What would happen if v is equal to c?
Well, if v is equal to c, then we have the denominator is the square root of 1 minus 1, square root of 0.
Yeah, so the Lorentz factor blows up. We get a 1 over 0 situation, and that's very bad.
Yeah,
And
we don't like 1 over 0.
no, and this also suggests something, that you cannot take some object that starts out at a speed less than the speed of light and accelerate it up to the speed of light, because if you did, you would cause this Lorentz factor to blow up. The math is sort of saying, "Oh, no, you don't." Right? You can't go that fast.
That's pretty cool. So that's why the speed of light is that universal speed limit.
And if you somehow thought you were going to go faster than the speed of light, now v squared is bigger than c squared. So v squared over c squared is bigger than 1. Where does that take us?
The square root of 1 minus something bigger than 1. So we end up asking the math to take the square root of a negative number.
Yeah. And now the Lorentz factor becomes complex. It's imaginary.
Imaginary? Did you hear that, Lord Flap and Quack? It's imaginary, just like us.
So the math is definitely saying something bizarre happens if you thought your velocity was at or above the speed of light.
Yeah, I'm glad we took this little detour and you explained the Lorentz transformation like this, because when you said it's worth talking about, in my head, I was like, oh God, this is going to be hard. But it actually makes sense and it's kind of cool.
And it also sheds light on these two notions that people have undoubtedly heard about, which is time dilation and spatial contraction. And if velocity equaled the speed of light, the Lorentz factor would blow up to infinity, which means as v gets faster and faster and faster, this Lorentz factor is becoming bigger and bigger and bigger. What the upshot of this is it tells you that the faster you go, time in one of these two reference frames is starting to slow down and it's accelerating in the other one. And so this explains mathematically this phenomenon of if you get on an interstellar spacecraft going incredibly fast, time is slowing down for you. Everybody you've left behind on planet Earth is getting old real quick. And that's because of time dilation.
Yeah, I think I remember that from the movie Interstellar. That happened in that movie.
It did. And Noah, we don't have to turn to sci-fi movies or imagine getting on, Battlestar Galactica or an interstellar spacecraft to have contact with this notion of time dilation. In fact, the cell phone that you have and I have and billions and billions of other people also have makes use of relativistic time dilation all the time. And that's because relativistic effects are at play in GPS satellites as they orbit the Earth.
Really?
Yeah. These GPS satellites are moving so fast that time travels slower on the satellites than it does on Earth. And if the satellites ignored this fact, they would never be able to give the precise GPS locations that they do. I read through a paper and I saw the numbers, and there's no way you would get down to, meter accuracy, let alone sub-meter accuracy, which is kind of a standard that people are targeting, right? You don't want your directions to be off by several hundred meters. That's no good, right?
No, no. Wow, that's pretty cool. I had no idea that the GPS satellites that we rely on every day are moving so fast that they have to take this kind of mathematics into account.
Yeah, and so, it may sound fanciful, all of these, Einstein thought experiments where, you're driving in a car that's going near the speed of light, you turn on a flashlight and time slows down and all. You know what? All of that stuff, all of those so-called Gedanken experiments actually make it possible for us to have these beloved devices that we take with us everywhere we go. So, pretty awesome.
Yeah, definitely. But how does all of this tie into the definition of space-time that you gave when we started this conversation? You called it something like a four-dimensional smooth mannequin with a Lorax metric and some curvy tenses.
Actually, Noah, there are no mannequins in space.
Oh, okay. Then how do interstellar travelers know what clothes they want to buy?
I actually have no idea, but I do know this, that the notion of a space-time manifold, in other words, a four-dimensional smooth manifold with a Lorentzian metric and a curvature tensor, relies on the presence of gravity. And although I didn't mention it explicitly before, everything we've been talking about with Einstein's theory of special relativity ignores the effects of gravity. Everything is taking place in inertial reference frames. And as soon as we throw gravity in, things start to get complicated.
Oh, now it starts to get complicated?
I know. The funny thing here is that although gravity is definitely the most familiar force in the universe, it's actually the one we understand the least.
But I've never seen anything to make me believe there's one all-powerful force controlling everything.
But 10 years after introducing his special theory of relativity, Einstein published another groundbreaking paper, and this time on what he called the general theory of relativity. And in that work, gravity definitely plays a role. In fact, it's what causes space to bend, and that's what gives us curved spacetime.
Okay, wait a minute, back up. Curved space-time. I think that sounds like a topic for another episode.
I think you're right. Our listeners definitely have enough to think about already.
I agree. But I want to thank you, Pete, for another great conversation. I think it was relatively cool.
Okay, I see what you did there. I think our listeners know that now is the time and this is the space for an excellent conversation about math.
Absolutely. So we hope you also got a lot out of this math club, and we will see you next time.
Bye, everybody. Take it easy.